These are the problems that we looked at on reflection and refraction. First problem is about photographing a hummingbird, and for this particular problem you don't really actually need to know anything about cameras, but the problem says you look through a camera toward an image of a hummingbird in a plane mirror. The camera is 4.3 meters in front of the mirror, so I'm going to just sketch the arrangement of the various items that they're telling us here. So here we have a mirror side view. There's a camera that is 4.3 meters in front of that mirror. The bird is at camera level 5 meters to your right and 3.3 meters from the mirror. Alright, so I'm actually just going to extend my mirror down there. So this looks somewhat realistic. So 3.3 meters in front of the mirror, about 5 meters to your right. Somewhere there is a hummingbird, and you are taking a picture of the image in the mirror of that hummingbird. So the image of the mirror is going to be behind the mirror, same distance away from the mirror. And let's label our distances here. 3.3 meters. This is 5 meters away from you. And because it's a plane mirror, we know that the image of the hummingbird is 3.3 meters behind the mirror. So, what is the distance between the camera and the apparent position of the bird's image in the mirror? We're trying to find this distance right here. That forms a nice triangle right here. This length of the triangle is 5 meters. This is 3.3 meters to the mirror, and then another 4.3 meters to the camera. So we have a triangle in this situation that is 5 meters on one side and 7.6 meters on the other side, which means we can solve for this apparent distance, or this distance between the camera and the apparent image, using the Pythagorean theorem. So that distance is the square root of 5 meters squared plus 7.6 meters squared. And that gives me about 9.1 meters. Second problem also involves a plane mirror. It reads, the figure shows an overhead view of a corridor with a plane mirror M mounted at one end. And I don't know how well this is showing up on a black and white printout, but this little section right here is the mirror. Go ahead and color that in so we can see that a little bit better. A burglar, here's the burglar, sneaks along the corridor directly toward the center of the mirror. If these distances are all 3 meters, how far from the mirror will she be when the security guard S can first see her in the mirror? Well, I think it's helpful in this situation to trace where light is coming from that can be seen by the security guard from the mirror. So what I do is I want to think about the rays that bounce off the edges of the mirror and make their way to the security guard from those edges of the mirror. The law of reflection tells us that the angle that you hit the mirror at is the same as the angle you're reflected at. So that means, I don't know where, somewhere in this neighborhood, if we match those angles, the light that hits the mirror on the right edge will come from right about here. And the mirror, the light that hits the mirror on the left edge will be coming from over here. What does that mean? Well, that means from the security guard's position here, the security guard can see anything that is in this little shaded region, but you're unable to see a reflection of something, for example, that's at the current position of the burglar. So it's not until the burglar comes and crosses the line, actually, right here, that the security guard is going to see the reflection of the burglar in the mirror, which should be after, if the security guard doesn't move, the burglar is seen directly by that line of sight to the security guard. But we'll humor the problem here. If this burglar is walking along this line, and these are all 3 meters, this is going to be a 45-degree angle of reflection over here, which means this is a 45-degree incident angle. And since this is half of the distance d, 3 meters, this is half of the distance d as well. And so the distance that the burglar is from the mirror when her reflection is first seen in the mirror is 1.5 meters. Next couple of problems we looked at involved curved mirrors. And I pulled this from a different book, so this notation in terms of labeling object and image distance is different than the notation that I use, and mine is in turn different from Knight's notation, so you kind of have to read the problem and understand what each of the symbols are standing for depending on which source you're getting this from. But here, P is being used for the object distances and I is being used for the image distances. The question reads that an object is placed against the center of a spherical mirror and then moved 70 centimeters from it along a central axis as the image distance I is measured. The figure gives I, the image distance, versus object distance P out to a distance of 40 centimeters. So this is 40 centimeters, which means this must be 30, 20, 10. What is the image distance when the object is 70 centimeters from the mirror? So one way we could do this is if we could figure out the shape of that curve, we could just keep extending it out to the right and figure out where we would cross the 70 centimeter line. However, this is possible to solve algebraically as well. Curved mirrors, as we discussed in the lecture or in the textbook reading, follow a mirror equation, and that mirror equation says that 1 over the focal length of that mirror is equal to 1 over the image distance, or the object distance, and I'm going to use P here to match the notation in this problem, plus 1 over the image distance. Doesn't matter actually which order you put those two terms in, but we have that expression right there. And so we can actually figure out the focal length if we know the image distance and object distance at some point. So I'm going to look on the graph for a place where it seems to cross at some axes I know the value of. And it appears that right here, the object distance is 15 centimeters and the image distance is minus 10 centimeters. The fact that the image distance is negative is telling us ultimately that we are forming a virtual image, but in most cases, mirrors form virtual images behind the mirror where light is not actually located. So let's go ahead and solve for the focal length. This is 1 over 15 centimeters plus 1 over negative 10 centimeters, and we invert that. And if you punch that on the calculator or even do the math in your head, 1 over 15 is the same as 2 over 30 plus negative 3 over 30 gives you a negative 1 over 30. The inverse of that is negative 30 centimeters. And the fact that it's negative tells you that this is a convex spherical mirror. which is forming virtual images that are smaller than the objects that they are reflecting. Then we can go out here to 70 centimeters and repeat using this mirror equation again, but now we're looking for the image location. So the image location is going to be 1 over the focal length minus 1 over the object distance, all inverted. So this is 1 over negative 30 centimeters minus 1 over 70 centimeters. Inverted all of that again, and we find that is negative 21 centimeters, which seems reasonable if you just think about extending this curve down and out for another 30 centimeters to the right. Negative 21 seems a reasonable number to find that image distance location. That was one curved mirror. Here's another curved mirror. A concave shaving mirror has a radius of curvature of 35 centimeters. It's positioned so that the upright image of a man's face is 2.5 times the size of the face. How far is the mirror from the face? Well, so we're going to have a concave mirror here. Somebody is looking in this mirror and seeing an image that is 2.5 times the size of their face. Over here. How far is the mirror from the face? Well, what do we know? We know that the radius of curvature of the mirror is 35 centimeters, and the focal length of a curved mirror is 1/2 the radius of curvature, so in this case it is 17.5 centimeters. We also know that because this is a concave mirror, the focal length is going to be positive, where at a convex mirror the focal length would be taken to be negative. We also know that the image is 2.5 times the size of the face, so that means the magnification is 2.5. Magnification is taken to be the ratio of the height of the image to the height of the object, and that's also the same ratio of the negative of the image distance to the object distance. And the sign of magnification ends up telling you whether the image is upright or inverted. But from this, we can find a relationship between the image distance and the object distance. The image distance is going to be negative 2.5 times the object distance. If we use that and the mirror equation, which says 1 over the focal length equals 1 over the object distance plus 1 over the image distance, we can solve for the object distance, which is how far this guy is from the mirror, by substituting in here and rewriting this as 1 over the object distance minus 1 over the magnification times the object distance. So I can pull 1 over the object distance out of here and get 1 minus 1 over the magnification. And now if I do a little bit of rearranging to solve for the object distance, I'm going to have the object distance is equal to the focal length times 1 minus 1 over the magnification. Now we can go ahead and plug in numbers. 17.5 centimeters times 1 minus 1 over 2.5, and that ends up being 10.5 centimeters that this person is away from the shaving mirror. That means the person is closer to the mirror than the focal length of the mirror, but that's actually important. Concave mirrors like this have the property that if the object is closer to the mirror than the focal length, it produces a virtual image, an image behind the mirror that is both larger than the object and upright. Whereas if the object is outside of the focal length of the mirror, the image is inverted. And I don't know if you ever did this when you were a kid when you were bored, but if you look into the concave surface of your cereal spoon, your image is flipped and small when you're far away, but then if you get really close to the spoon, suddenly your image will flip and be upright and be larger than the object itself. Finally, we looked at a couple of problems that involved refraction, and Snell's law comes in when we're dealing with refraction. This problem, eyeing a tank, reads when the rectangular metal tank in the figure here is filled to the top with some unknown liquid. Observer O, with eyes level to the top of the tank, so observer O's eyes are over here, looking this direction, can just see corner E of the tank down here. A ray that refracts towards O at the top surface of the liquid is shown. If we know that this is 85 centimeters and this is 1.1 meters, then what's the index of refraction of the liquid? Well, the key to solving these refraction problems is Snell's law, and Snell's law in a pretty general form says the index of refraction in one material times the sine of the angle relative to the normal in that same material is equal to the index of refraction in a second material times the sine of the angle in that second material. Well, N1 is going to be the index of refraction of air. Sine theta 1 is going to be the sine of the angle out here in air, but relative to the normal, this is a 90-degree angle. N2 is the index of refraction of this liquid. It's what we're trying to find. And sine theta 2 is the sine of this angle right here. So there's a number of ways you can proceed. You can figure out what that angle is. I'm going to take advantage of the fact that sine of any angle is the ratio of the opposite side to the, not adjacent, the hypotenuse side. And the opposite side in here, in this particular triangle, is L. The hypotenuse, I got to use Pythagorean theorem, is square root of L squared plus D squared. And I'm going to plug that in for the sine over here. This is L over the square root of L squared plus D squared. So that means the index of refraction of the liquid is equal to the index of refraction of air times the sine of 90 degrees over L over square root of L squared plus D squared. Index of refraction of air is about 1. Sine of 90 is about 1. So this is going to end up being 1 times the square root of 1.1 meters squared plus 0.85 meters squared all over 1.1 meters. And if I punch that into my calculator, I find that the index of refraction of this mystery liquid is 1.26. One check when you're solving problems like this is that because light slows down in any material that's not a vacuum, even though it doesn't slow much down in air, and so we use an index of refraction for air of 1, because it slows down in every other material, water, oil, whatever, the index of refraction is always going to be greater than 1. And we just Googled this yesterday in class. The highest known index of refraction of any material is somewhere in the ballpark of 2.6. So all the indices of refraction you should be solving for are going to be somewhere between 1 and 2.5, and that's a good thing to keep in mind when you're checking the reasonableness of your answer. Final problem that we looked at involved a glass slab. It reads, light in a vacuum is incident on the surface of a glass slab. If In the vacuum, the beam makes an angle of 32 with the normal to the surface. So here is glass, and here is vacuum. And relative to this normal line, light makes a 32-degree angle. Well, in the glass, it makes an angle of 21 degrees with the normal. So it's 21 degrees over here. What is the index of refraction of the glass? Well, Snell's law says the index of refraction in the vacuum times the sine of the angle in the vacuum is the index of refraction in glass times the sine of the angle in glass. That means the index of refraction in glass is the index in the vacuum times the sine of the angle in the vacuum divided by the sine of the angle in glass. That's 1 times the sine of 32 degrees divided by the sine of 21 degrees. And if you punch those numbers into a calculator, you get out 1.48. So those are the problems we looked at in class. Hopefully that, along with either the lecture or the textbook reading or both, sets you up for successful work on the next problem set. As always, if you've noticed any error in these solutions, I'd appreciate you letting me know that. Thank you.